Well, I have a laptop here, and so I am going to actually record this video with it in my lap, which I don't normally do, but I'm watching the Alabama LSU football game. Um, so we're going to talk about calorimetry, but let me back up for just a second and just talk about some of the other things that we've been, just something else that we've been talking about immediately previously to this, which is enthalpies. And so we talked most recently about enthalpies of reaction and how you can use enthalpies of reaction to calculate the amount of heat absorbed or released when a certain amount of a particular reactant is used, etc. So here's an example of this. The enthalpy of combustion for 1 mole of methane is minus 890 kilojoules. And so what that means is that if we take 1 mole of methane gas and we combust that in a balanced equation like this, delta H is minus 890 kilojoules. Well, there's another set of reactions that we see just sort of in the world around us that have specific enthalpies of reaction associated with them, and that would be just nutritional information that you get on the side of your cereal box. So one serving of Captain Crunch contains 110 big C calories, or that would be 110 kilocalories or 469 kilojoules of energy. And so there you go. There it is. Captain Crunch, 110 kilojoules. The question is whether it's this number, negative 890 kilojoules for the combustion of methane, or this number, 100 big C calories for Captain Crunch. Where do these numbers come from? How do we actually come up? How do we actually come up with these numbers? Well, we do that using a process called calorimetry. And so again, we're going to ask the question, where do these numbers come from? Well, we're going to run the reaction, and then we're going to measure the energy change of the surroundings using calorimetry. In other words, we're going to run a reaction. The system is either going to gain or lose potential energy in the form of enthalpy, and it's going to either transfer to or absorb from that energy to or from the surroundings. So we can measure the energy changes of the surroundings to figure out the energy change, the potential energy change for the reaction. And so let me just quickly show you a little clip. This is actually from a morning news show, and this is food calorimetry, although in a little bit of a not particularly scientific way of doing it. But here we go.
End of the road for me, right, folks.
Go ahead and light that thing up. Don't bring it over quite yet. Get ready. All right, bring it over and hit them. Hit it and hold it there. All right.
Did I do it too soon?
No, that was great. So now you're getting a sense of how much energy there are in those toasted oats. They're really toasted at this point, right? Very, very, still going. Very, very bright flame.
Yeah.
All right, let's try it with the cheese puffs.
Okay, now do I need to hold it on there longer or a little bit less?
No, you did actually really well.
Okay.
That was pretty good. And, we don't want the smoke alarm to go off, so we'll cover that up. All right, so go ahead and light up your torch again.
All right.
So this is the comparison. This is the cheese puffs. Let me get the oxygen in there. Go ahead and hit them. Hold it there for a second. Okay, pull back.
Oh, wow.
Okay, see, that's why I brought the fire extinguisher as well.
Sure.
Incredible amount of energy coming off those cheese puffs.
You can feel the heat.
Okay, so like I said, that was rather non-scientific, but what they're doing there is essentially showing the difference in energy between a bowl of Cheerios and a bowl of cheese puffs. And what he was pouring on there, by the way, was not like fuel for the fire. He was just pouring on liquid oxygen to make sure that the reaction had enough oxygen to go really vigorously. Okay, so where do the numbers come from? We run the reaction and we measure the energy change of the surroundings using calorimetry. So we talked about that. Here's a typical sort of calorimeter that we could actually use in a reaction, and we will do this in a reaction in this course later this week. And so this is what's called a coffee cup calorimeter. And so you have a couple of nested styrofoam cups here. I've got these in the lab. You have something that's also insulated in the top. Here it's cork. What I actually have is just some styrofoam lids. And then you have a thermometer that goes through. I don't have spiffy stirring rods like this, so we end up just having to swirl the cup to make sure that everything gets mixed properly. And so we're going to measure, and so in this case, because this is a reaction occurring in aqueous solution, the system is going to be whatever reaction we want to do. The surroundings are actually going to be the water. And so by measuring the temperature change of the water, we can measure the energy transfer between the system and the surroundings. And so it just basically works like this. We run the reaction in a closed system. In this case, it's going to be the coffee cup calorimeter that we just looked at. We measure the change in temperature of the surroundings, and for a reaction run in a coffee cup calorimeter, we treat the water as the surroundings. And then we can calculate the enthalpy of the reaction. One question that raises is, how do we convert the temperature change of the surroundings into enthalpy in joules? Well, it turns out that every pure substance, including water, which is the surroundings that we use in a coffee cup calorimeter, has a physical property known as its specific heat or heat capacity. And you can see this for various substances here: nitrogen gas, aluminum, iron, mercury, water, methane, carbon dioxide, calcium carbonate. So for water, it turns out to be 4.184 joules per gram joules per gram Kelvin. What does that mean? It means that it takes 4.184. They've got it rounded to three significant figures here, but it's 4.184 joules. And the reason it's that number is because the original definition of a calorie was the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And so it takes 4.184 joules of energy to raise a gram of water by 1 degree Celsius. And therefore, if we know how much water we have in the cup, and we know its specific heat capacity, and we know the change in temperature of the water, we can simply multiply this together to get the energy change in joules. Let me just go back to one particular point here. In the gas law chapter, we talked a lot about how everything has to be in kelvins when we are doing these calculations. Why is it possible to do it in either kelvins or degrees Celsius when we're talking about calorimetry like this? That's because temperature changes are the same in degrees Celsius as they are in kelvins. So a Celsius degree and a Kelvin have the same magnitude. And therefore, if I raise the temperature of a thing by 5 kelvins, from 298 kelvins to 303 kelvins, I'm also raising its temperature by 5 degrees Celsius, from 25 degrees Celsius to 30 degrees Celsius. So changes in temperature are the same in kelvins as they are in degrees Celsius. Right, so we have specific heat capacity, or specific heat, as being the amount of energy required to raise the temperature of a gram of something by 1 degree Celsius. So for example, here they're given the example again of water. If I've got exactly 1 gram of water at 14.5 degrees Celsius, and I put in 1 calorie, or 4.184 joules of heat, I raise its temperature to 15.5 degrees Celsius. So what do we do here? We've got this system. We run the reaction. We know how much water there is in the cup because we measured that beforehand. Typically, the way you do that is you measure the cup, you weigh the cup empty, or zero the cup on the balance, and then put a certain amount of water inside, and you weigh that so you know how much water you have. We run the reaction and measure the temperature change of the water, and then we use the specific heat of the water to calculate the enthalpy change. So specific heat is defined as the heat transferred divided by the mass of the substance that's being heated multiplied by its temperature change. And so that just comes down to S is equal to Q, the heat transferred, over the mass of the substance times its temperature change. And you can rearrange that so that Q is equal to M times S times delta T. Now, some textbooks actually use C instead of S for specific heat. It just had to do with C related to calorimetry. And so sometimes it's easy to remember Q equals MCAT, MC delta T. This textbook uses S as the symbol for specific heat. All right, so once again, we've got our calorimeter. We carry out a reaction in aqueous solution. We can measure the heat we can measure the temperature change of the water, which is the surroundings, and that allows us to calculate the energy transferred in that reaction. Because we know the specific heat of water, which is 4.184 joules per gram Kelvin or joules per gram degree Celsius, we can use this equation to determine the value of Q. And because the process is occurring at constant pressure, then Q is equal to delta H. And so let's take a look at another video which shows something very similar to an experiment that we're going to do in our class. And this is just using a coffee cup calorimeter.
A coffee cup calorimeter can be used to measure the enthalpy change accompanying a chemical reaction. It's a very simple apparatus. It consists of two polystyrene coffee cups nested within one another. We can set the coffee cup calorimeter up on top of a clamp stand, and then into the coffee cup calorimeter we can insert a thermometer. And the longer the thermometer, the more accurate our measurements are likely to be. And we can include a lid, all of which will serve the purpose of ensuring that the heat produced during the chemical reaction stays inside the coffee cup. We have previously measured the mass of the empty coffee cups and then added approximately 100 milliliters of hydrochloric acid and then remeasured the mass of the coffee cups with the hydrochloric acid. The difference of those two measurements gives us the mass of the hydrochloric acid, and that can be done on a top-loading balance. On an analytical balance, we have weighed out about 0.6 grams of magnesium oxide in a small weighing boat. With our coffee cup calorimeter set up, we should wait 3 minutes to allow the temperature to equilibrate, meaning that the temperature should not be moving. And at that point, we can then add the magnesium oxide to the hydrochloric acid. Be sure to do this quantitatively to make sure we add all of the magnesium oxide. It's then good practice to stir the solution to make sure everything mixes together, and then we should record the temperature from the thermometer every 20 seconds, and we should do that until the temperature starts to go back down.
Okay. So that is very similar to what we're actually going to do in class. So for that particular demonstration that he was doing, again, we used the Q equals MCAT, or Q equals M times specific heat times delta T. In his case, he mentioned that they had weighed out 100 grams of the solution. The specific heat of that solution is 4.184 joules per gram degree Celsius. Unfortunately, he doesn't indicate in there what the temperature change was once the magnesium oxide had been added in. But if he had done that, then we could have actually calculated from that video the heat transferred in that particular process. Now, another thing we can use calorimetry for is to kind of use it in reverse, and that is to determine the specific heat capacity of a substance. In other words, before we can use a substance like water to its specific heat to do calorimetry, we need to use calorimetry to determine water's specific heat. And so here's a typical problem. This comes right out of test bank for this chapter. An 8.29 gram sample of calcium carbonate absorbs 50.3 joules of heat, upon which the temperature of the sample increases from 21.1 degrees Celsius to 28.5 degrees Celsius. What is the specific heat of calcium carbonate? Okay, well, we can rearrange this now so that we're solving for specific heat instead of solving for Q. It gives us the value for all three of these things. It says that Q, or delta H, is 50.3 joules. It says that the temperature increases from 21.1 to 28.5, so that difference is 7.4 degrees Celsius. And it gives us the mass of the sample, which is 8.29 grams, and we can calculate the specific heat of calcium carbonate to be 0.82 joules per gram degree Celsius. All right, now that is for reactions that we can run in aqueous solution. There are a lot of things that we can't do in aqueous solution, including things like combustion. And so, in fact, if you were going to do if you were going to do food calorimetry, like we saw in that video earlier, you would actually do this. That requires combustion. You would actually do this in what's called a bomb calorimeter. A bomb simply just means it's a closed container. And so you would put your Cheerios into this little tiny thing inside here, which also has a spark source. Your Cheerios would burn. That heat generated by the Cheerios burning would heat up the water in here, and then you've got a thermometer that allows you to measure the temperature change of the whole system. So the heat absorbed or released, and typically you're going to use a bomb for combustion, so it's essentially always going to be released, is a very good approximation of the enthalpy change for the reaction. It's not 100% exact. That's because this is occurring not at constant pressure. It's occurring at constant volume. And so what we're really measuring is not delta H, we're measuring delta E, but they're very, very close to each other. And so this works very well for determining the enthalpies of things. Now, here's the thing about a bomb calorimeter. It's made up of a lot of things. It's not just made up of water, insulated water like a coffee cup calorimeter. It's got water, it's got the stirrer, it's got the reaction vessel, it's got these wires, it's got a little cup inside for the sample to be in. So we can't just use one specific heat to calculate the energy change for a bomb calorimeter. It's more complex than that, and so we'll talk about this rather than trying to do it in the video. We'll discuss this in class. And so the QOD itself will be related to the things that we talked about earlier in this video, which is just the basic principles of calorimetry, the idea about how a coffee cup calorimeter works, and then applying that equation, Q is equal to mass times specific heat times delta. Okay, that's the end of the video. Thanks for watching.